Hello everyone. So today we begin the first lesson in Unit 2, which is the preliminaries of inferential statistics. And we're going to start by talking about probability, which is very, very important in inferential statistics. And we're going to start with the basics. Here's an overview for the whole unit. Today we're going to introduce basic probability concepts, and then we're going to talk about two basic rules and probabilities and contingency tables. Then after that, we're going to talk about random variables, focusing on discrete random variables and their parameters. Following that, we're going to look at two examples of random variables, which is binomial and Poisson. And then we're going to talk about continuous random variables. And then in the sixth video of this unit, we're going to talk about sample means and the central limit theorem. Very important concepts. And then in the last video, the seventh video of this unit, we're going to look at point estimates and confidence intervals. Okay, and then after that, we'll have our second of three celebrations of knowledge. And that's just going to cover section 3.1 to 8.3. All right, let's dig in. The goals of this lesson are to understand what the probability of an event means, and we'll talk about what an event is. Know some ways of coming up with the probabilities. There's three ways we'll talk about. Know important terminology about probability, and then, lastly, and, or, and complementary events. So that's what we have in store. Okay, so at this point, just think of an event as just, something that could happen. The probability of something happening is a quantification representing how likely it is that the event will occur. So by the end of the semester, we're going to have talked about inferential statistics, which is a way of leveraging math and data to make decisions and conclusions. In order to do that, we need to quantify likelihood, and probability is a way of quantifying likelihood. The probability of an event is a number between 1 and 0 inclusive, where roughly speaking 0 indicates impossibility of the event and 1 indicates certainty in the event's occurrence. The higher the probability of an event, remember it can't go above 1 though, the higher the probability of the event, the more likely it is that the event will occur. When is probability used? All the time. Quantifying likelihood is very important. Think about risk management. The insurance companies spend millions and millions, if not billions of dollars in risk assessment and management. Decision making. In the real world, we need to make decisions in the presence of uncertainty. That's exactly what finance and the stock market is all about. Making decisions in the presence of uncertainty. And so that uncertainty needs to be quantified, and that is what probability is. And then we want to optimize outcomes on average. Very complex questions. And we are just going to scratch the surface. Okay, quantifying probability. So first we need to formulate the solution. We've got some terminology here that's going to be used throughout. By the term experiment, I mean a planned activity carried out under controlled conditions. So that's an experiment. Outcome. An outcome is a particular result of an experiment. The sample space is the set of all possible outcomes of an experiment. An event is a subset of the sample space, i.e., that is a group of different possible outcomes. So that's what we mean by an event. It's a collection of possible outcomes. Quantifying probability, there's three common approaches. The first is theoretical, in which we use logic, reason, and math to determine probability. This right here is the least accessible way of computing probability. However, it is the most accurate. Empirical. So there's this empirical approach. It uses past data to estimate true probability. This is fairly accessible and fairly accurate. Subjective. This is using personal experience and feelings to guess the true probability. And this is the most accessible, but the least accurate. Now, all of these are ways of trying to determine the true probability. There's some true probability that something will occur, but it's impossible to get to, and so we use theoretical, empirical, and subjective means to approximate it. All right, let's talk about that first approach, theoretical. So what you have is given assumptions. Remember, this is the least accessible or practical. You have to make lots of assumptions in order to apply math to this in general, very complicated thing to understand. So what we do is we compute the probability based on theories such as physics, geometry, symmetry. Each outcome should be as equally likely as the others. Okay, let's take an example. Compute the probability of rolling an odd number on a 6-sided die. Okay, so the experiment is one roll of a 6-sided die. The sample space is the set of all outcomes. There's all the outcomes that can occur on a 6-sided die. And the event that we're talking about here is an odd number. So 1, 3, and 5. Now, notice that each one of these, because of symmetry, all right, a dice is very symmetric. Each side is as big as the other. And so we would expect that each side would have an equally likely chance of appearing on top, assuming that the die is fair and well constructed, which it doesn't say we're assuming that, but let's just go ahead and assume that for the purpose of this example. The die is fair and well constructed. And so what is the probability of this event? The event has 3 possibilities out of a total of 6. And so the probability of this event, let's call it A is that event, the probability of that event occurring, is going to be 3 over 6. 3 possibilities out of 6. And so that equals 1/2. Okay, quantifying probability. Now we're going to talk about the empirical approach. And in contrast to the theoretical approach, I did not do any data. I didn't actually roll a die at all. It all just came out of my brain. This sample, reasoning through the symmetry of the die, making the assumptions, and computing the sample space, all of that just came from my brain. It was theoretical. Empirical now. Okay, so given data, this one requires data. This is also called the relative frequency approach. The way you compute this is you take the number of trials with the outcome in event. So if the outcome is in the event that you are interested in, take that trial and add it to the tally. Then what you do is you divide by the total number of times trials was performed, and you divide that. Practical example here. What is the probability Tyler Karchner will make a field goal? All right. And so I went on SVU Athletics homepage and found this field goal percentage. The way that a field goal percentage is computed is you have somebody, in our case it's Caden Nicholson, and he will see every time Tyler attempts to make a field goal, he'll mark that down. And every time that is successful, that counts as a success. And so in Tyler's case, from all the games that he's played, he has had 111 successful field goals after only attempting it 193 times. And so that comes to this percentage. So this right here is the number of events that was in the particular outcome. The outcome was scoring points. And this right here is the total number of times that trial was performed. So if Tyler's going to attempt to make a field goal, there's a 57% chance, 57.5% chance that he'll score some points. Okay, there's also this subjective probability, which basically just uses your own feelings and past experiences. You just kind of reflect on it, and it's very accessible, right? Because you don't need anything to do this, but it's the least accurate and the least principled way of coming up with a probability. So an example: what is the probability of a college student athlete dying from COVID? And your experience might be different from mine, but based on my experience, that probability is extremely small, by 0.000001. Let me just put that down. So 0.000001, something like that. This approach isn't used all that often because it's not accurate enough, but it does get used. What is the probability of an 80-year-old dying from COVID? Now, this probability is also fairly small, but it's not as small. And so I don't know. I'd like to say maybe 0.00, maybe 0.01, maybe just 3 zeros, the 100th%. So if that were true, then that means what? 1 in every 10,000 80-year-olds died of COVID. And that seems maybe a little much. But I don't know. Anyway, and that's just subjective. Okay, more terminology. Independent events. When the occurrence of one event has no effect on the probability of the occurrence of another event. So they just don't have any effect on each other. Example. Example. A meteor striking the moon today and me having cherry yogurt for lunch. There's no way they're related. There's just no relation there. Okay, mutually exclusive events. Now these are events that cannot occur at the same time. And that would be like this. So an example of this would be me having cherry yogurt for lunch today and me having no lunch today. They are mutually exclusive. If I ate some cherry yogurt, I had some lunch, which is not no lunch. And if I had no lunch, I could not have had any cherry yogurt for lunch. So those just cannot happen at the same time. Okay, quiz. So here's a little quiz. So fill this out, and I and the TA will be looking at these. So we now want to talk about ways of combining events, making things a little bit more complicated, which is important because the world is complicated and we want to try and model it as best we can. So you've got and events, or events, and complementary events. And events. The event A and B, written A intersect B, there's, is the set of all outcomes in both A and B. Here's an example. The event A is I get an even number on a single roll of a 6-sided die, so that would be even number. B is I get a number less than 5 on a single roll of a six-sided die. So the experiment is a single roll out of a 6-sided die, and the event A is the outcomes 2, 4, 6. Those are the only even number that can be outcomes. The event B is going to be 1, 2, 3, or 4. Those are the only numbers that are less than, not less than or equal to, less than 5. And so what is A and B? Okay, so A and B, A intersect B, A and B is going to be the events that are in both. So that's going to be 2 and 4, and that's it. So 2 is in both, and 4 is in both. 1 is not in both, 3 is not in both, and 6 is not in both. So those are not in A and B, or A intersect B. Okay, so what's the probability of A intersect B? So that's going to be 2 over 6. So the 2 there is the total number of outcomes, is the total number of outcomes in A intersect B, A and B. There's only 2 outcomes, and the total number of possible outcomes is 6. So that's going to be the denominator. Or events. The event A or B, written A union B, is the set of all outcomes in either A or B or both. Okay, back to our example. Same example as before. So A equals 2, 4, 6. B equals 1, 2, 3, 4. And now A or B is going to be the set. All right, let's see. It could be in A or B or both. So 1 is in B. 2 is in both. 3 is in B. 4 is in both. 5 is not in either, so that one can't be in this union. But 6 is in A. That's in A or B. It's in A. So that is A or B. So that's that right there. What is the probability of A union B? So the probability of A union B is going to be 5, because there's 5 total here, over 6, which is the total. So that's 5 over 6. Okay, complementary or opposite events. The complement of a given event is the event that the given event does not occur. So it's all of the outcomes that are not in the given event. Okay, so example, A, and let me just write that out. Not A is going to be all possible outcomes that are not in A. And it's very good to think about events as a list of outcomes. Okay, example, A is get an even number on a roll of a single-sided dice, just as before. Not A, okay, so A is equal to 2, 4, 6. Those are the even numbers. Not A is going to be to get a 1, so this is not A, is going to be to get a 1, a 3, or a 5, because those are all of the numbers from the total, all 6 possible. Those are all the numbers that are not in A. And that amounts to just getting an odd number. So it's the opposite, you might think. So there it is. Not A is sometimes read with a minus sign in front of A. Sometimes it's written like A prime. I think actually the book uses A prime. So let's go with that. It's A with an apostrophe after it. That's not A. Okay, so complement rule. A, the probability of A, what do you guys think? The probability of A plus the probability of not A is going to be 1. That's going to be everything. So this right here is this probability is the number of outcomes in A over total outcomes, plus this is the number of outcomes not in A over total. And if I add those together, I get all of the outcomes. Okay, that's a way of thinking about it if we could use the theoretical approach to the probability of A, which we can't always do, but the idea is the same. The probability of A not occurring is going to be 1 minus the probability that A will occur. Okay, one more rule. Suppose A and B are mutually exclusive. So they cannot happen at the same time. What's the probability of A and B both happening at the same time? The answer to that is 0. 0. They cannot happen at the same time. Recap. So today we introduced probability. We looked at key terms, and we looked at the 3 approaches for estimating probability: theoretical, empirical, which, to say in passing, is also referred to as the relative frequency approach, because it's computed by finding the frequency divided by the total number of occurrences, so that's the relative frequency. And then the subjective approach. We then looked at different types of events: mutually exclusive and independent. We also talked about compound events, and events, or events, complementary events, and that brought us to our very first rule, which is the probability of A not, or A prime, or not A, equals 1 minus the probability of A occurring. Okay, and that's all we need to talk about at this time. So everybody have a wonderful day, and we'll see you in class.